Okay, good morning. In today's session, I will be discussing about the proper cantilever subjected to uniformly varying load. So, propped at free end. The prop reaction. Yeah, with prop here at free end. So, in this case, I think we have discussed the case of point load, central point load. Okay. Now, we have the case of uniformly varying load with 0 at free end, intensity 0 at free end, and maximum W at fixed end. So, to solve this case, we will again make use of the same principle, that is the compatibility condition. Okay, because we know that the net deflection at B at the point of prop is 0. Okay, using this condition, we will find out the prop reaction R. Okay, yeah, for that, let us consider a section distant x from free end B. Here the intensity at this section is taken as W dash, which can be found out to be Wx by L, where W is intensity at fixed end and x is this distance. L is the span of the B. L is the span of the B. So by applying the similar triangle property, or by simply interpolation, we'll get this value of W dash. So similar triangle property says the ratio of corresponding sides is same. The triangle, this triangle and this triangle, these two are similar. Hence, the ratio of corresponding sides. Which sides are corresponding here? W dash corresponds to W. X corresponds to L. Okay? So, the ratio of W dash by W is equal to X by L. Or W dash is equal to W into X by L. That's what is taken here. Now, to find deflection at B due to the uniformly varying load, because we consider this as the combination of two loads acting on cantilever. One is uniformly varying load and the other one is prop reaction acting upwards. So due to this uniformly varying load, we will have a deflection of delta 1, say, which is in the downward direction, and due to prop reaction R, we will have upward deflection delta 2, which is in the upward direction. Upward deflection delta 2 will have 3. Okay, so the condition is delta 1 is equal to delta 2, or delta 1 minus delta 2. The net deflection at B is equal to 0. Net deflection at B is equal to the prop reaction R. Okay. So, first, to find deflection, let us consider deflection delta 1. Okay. Consider a section x here at a distance x, and moment at this section x is, from this figure, moment at section x is moment due to this varying load. So what is the moment of that load? So area of the triangular load, the intensity Wx by L into x base by 2. That is the area. And centroidal distance of this from section x is x by 3. So moment of this area about x-axis, about the axis x, section x is w x by L into x by 2 into x by 3. That is the centroidal distance. So bending moment is wx cube by 6L. Wx cube by 6L. Now we substitute this in the expression ei d square y by dx square equal to mx. Actually, this should be taken with the negative sign being hogging. Being hogging moment, the bending moment is taken negative. Minus w x cube by 6L. Minus w x cube by 6L. Okay. So to find find deflection delta 1, we'll integrate this with respect to x. We'll integrate this equation with respect to x. So what will you get by integration? Wx power 4 by 24 L plus constant of integration C1. So how will you get C1 here? By substituting the condition x equal to L, dy by dx is equal to 0. At x equal to L, that means at end A, the slope is 0. At fixed end, the slope is 0. So using this condition, we will find out C. So what does this condition give? Ei dy by dx, that is dy by dx is 0. So left hand side will have 0. Minus w L power 4 by 24 L plus C1. Okay. Or C1 is equal to WL cube by 24. WL cube by 24. The condition will have Ei dy by dx is equal to minus Wx cube by 6L plus, what is C1? 24x by Wx power 4 by 24L. Wx power 4 by 24L plus WL cube by 24. C1 is WL cube by 24. Okay. Now you find out the integration again. You integrate this once again. You will get minus Wx power 5 by 24 into 5, 120 L plus WL cube by 24 into x plus C2, another constant of integration. And the value of C2 is obtained by substituting the condition at x equal to L, y is equal to 0. Because at fixed end, deflection also is 0. So using this condition, we will have minus WL power 4 by 120, substituting L for x, plus WL power 4 by 24 plus C2. So this gives C2 equal to, you multiply and divide with 5 here. So you will have numerator and denominator same. So it is minus, denominator will have 120 minus 5 WL power 4 plus WL power 4 or minus WL power 4 by 30. Here you will have 4 by 120, actually it is 1 by 30. So the equation now for y is minus Wx power 5 by 120L plus WL cube by 24L minus WL power 4 by 30. Okay. Yeah, taking this here, L power 4, it becomes WL cube x, isn't it? WL cube x here. In this equation, we will substitute C2. Okay. Now, this is the governing equation for finding out deflection at any point along the span. Now, we want the deflection at free end B, isn't it? So, for that, we substitute x equal to 0. So, by substituting x equal to 0, in the above equation, the deflection at B is taken as delta 1, isn't it? We called it as delta 1. So, EI delta 1 is equal to, in place of y, we substitute delta 1 equal to, putting x0, the first two terms become 0. So, you will have minus WL power 4 by 30. Or delta 1 is minus WL power 4 by 30 EI. So, here the downward deflection, and hence it is obtained with the negative sign. Okay. Yeah, delta 1 is magnitude, if you consider, it is WL power 4 by 30 EI, which is downward. Okay. And what we have, the condition we have here is delta 1 is equal to delta 2. And what is delta 2? The deflection due to point load at free end. So in this case, delta 2 is, we can take this as RL cube by 3EI. So we need to remember these results, some basic load cases. We need to remember the results so that we don't again need to solve for that. Okay. So you need to remember these cases. Point load, UDL and all, we need to remember. So delta 2 is RL cube by 3EI, which is upwards. So equating these two, equating delta 1 and delta 2. Delta 2 is RL cube by 3EI. And delta 1, the magnitudes only will consider here. Upward deflection and downward deflection. Both are equated, the magnitudes. So you will get R equal to WL by 10. WL by 10. So this is the prop reaction. And once you know the prop reaction, the next step is to analyze that for shear forces and bending moments along this span, Okay. So what will be the shear force and bending moment diagram for this? Shear force and bending moment diagram for this. So by considering a section along the section at any distance x, R, which is WL by 10, and this is W dash, which is Wx by L, and this is X. So shear force at section X is Wx by L minus WL by 10. The convention that we follow for shear force is right side downwards positive. Right side downwards positive and upwards negative. Right side upwards negative. So we have this varying load downwards. So Wx by L, actually it is area we have to consider. Total load Wx by L into x by 2, half into base into height, okay, minus WL by 10. That is WL square, x square by 2L minus WL by 10. Isn't it? So by substituting different values for x, we'll get shear force values, and we can plot the diagram now. Okay. For example, for x0, what is the shear force? Shear force at B. Substituting x0 here, this term becomes 0, and we have minus WL by 10. Minus sign here indicates it is upwards. Okay. The force is upwards. Similarly, at x equal to L, shear force at A, which is parabolic. This is parabolic variation. We have x square. Okay, at x equal to L, what do we get? WL square by 2L, that is WL by 2 minus WL by 10. That is 5WL, 4WL by 10 or 2WL by 5. Okay. So if you see the diagram now for this, minus WL by 10, and here it is plus W 2WL by 5. So in between it crosses the axis. That means the shear force becomes 0. It changes sign. Okay. And the point where it changes sign is obtained by equating the shear force to 0. So equating Wx square by 2L equal to WL by 10. Equating this to 0, you will have W cancels, okay? X square equal to 2L square by 10, or x equal to L by root 5. L by root 5. Okay. So it means the diagram will be something like this. X is measured here from B, which is L by root 5. At a distance of L by root 5, the shear force changes sign. Okay. Yeah. The shear force changes sign at a distance of L by 2 from free end B. Okay. Now, bending moment diagram also we can draw. What is the bending moment at X? We can draw the bending moment diagram considering bending moment at X. What is bending moment at X? Wx square by 2L into x by 3, the moment. Okay. This is negative, plus R into x, WL by 10 into x. Okay. And this is the bending moment equation. So substituting x0 we will have bending moment at C equal to B equal to 0. Okay, substituting x0 at x equal to L, you will get bending moment at A. What is bending moment at A? Minus WL square by 6 plus WL square by 10. Okay, here you will have minus 5 plus 3, that is minus 5 plus 3 into WL square common. So what is that? You are going to get minus WL square by 15. That is the bending moment at fixed end. Okay, bending moment at fixed end. Here the bending moment is 0. Here at fixed end it is WL square by 15. And you have a point here C where the bending moment is maximum positive. Maximum positive. Yeah, something like this. Because the point where the bending shear force changes sign, you will have maximum bending moment. So substituting x equal to L by root 5, you will get this maximum bending moment. So what is M maximum? Substituting x equal to minus W by 6L into L cube by 5 root 5. Into L by root 5 we are substituting here, plus WL square by 10 root 5. Okay, so what will you get here? WL square you can take common, 1 by 10 root 5 minus 30 root 5. 1 by 30 root 5. So multiply and divide with 3. You will have 3 by 30 root 5, 1 by 30 root 5. So you will have WL square by 15 root 5 actually. That is the maximum bending moment. Okay. By substituting x equal to L by root 5. Yeah. That's all for now. We will discuss another example with the uniformly varying load only, but this time it is varying from 0 at fixed end to W per meter at free end. Okay. The position is reversed. So we'll discuss this case later.
Like, share and subscribe. Hit the bell icon for more updates.